Hello, good evening everyone. Welcome to all. Today we are here for a talk by Dr. Amit. He will be taking talk on optics in a flatland. In this, he will give a brief about interaction of matter and light in the subwavelength regime. He will give what metasurfaces are and how to fabricate and how to integrate the metasurfaces in the nanophotonics chips. So I welcome our speaker, Dr. Amit Agarwal. Our speaker, our chapter advisor, Dr. Umesh Tiwari, sir, will introduce him in shortly. Now I like to inform you that you can post your question if you have any through the chat box. Your question will be taken one by one by our member, and if after that text question, then you can, if you have any query still pending, then you can unmute yourself and take the question. So and after, so the structure of our talk will be like sir will give his talk, then question answer, and then afterwards there will be end of the session. And Sinha sir has joined us, so welcome to him, sir. Now I like our chapter advisor, Dr. Umesh Tiwari, sir, to kindly introduce our speaker, Dr. Amit. Thank
you. Good evening to all the participants. I welcome all the participants on behalf of the SPIE CSIO chapter. I welcome today's speaker, Dr. Amit Agarwal. He's my friend and he's a pioneer in the field of metasurface and metamaterial. I take this opportunity to welcome Professor R.K. Sinha, our mentor and former director CSIO Chandigarh. It is a great pleasure and honor to me to introduce Dr. Amit Agarwal. Dr. Amit Agarwal is a project leader at NIST and an associate research scientist at the IREAP of the University of Maryland at College Park. He received his PhD in electrical engineering from the University of Utah, followed by a postdoc at NIST. He then joined the faculty of Syracuse University as the inaugural John E. and Patricia Breyer Professor in Electrical Engineering in the EECS department. His current research interests are focused on developing integrated nanophotonics device architectures operating from the ultraviolet to the infrared for quantum optics application, including atom trapping and frequency comms. He has been involved with the SPIE and on and off over more than a decade. He was a winner of their prestigious DJ Lowell Scholarship in 2007 and was selected as an SPIE Rising Researcher in 2018. He has religiously participated in the various conferences organized by the SPIE over the year, including Photonics Best and Optics and Photonics. He hopes to expand his involvement with the organization through various outreach activities such as this organized by them in the future. So the bio I have introduced whatever provided to me. Maybe he has a lot of other laurel and so many good publication and many awards in his credit. So with these words, may I now request Dr. Amit Agarwal to start his talk.
So let me try to share my screen. Could you confirm if you could see it and also see my laser pointer?
Yes, sir.
Try to transition once
Your
it works.
slide is visible.
Okay, fantastic. So let me first thank the SPI chapter and Keshav and Professor Tiwari for the kind introduction and for this invitation to speak. I was really hoping to visit their institute in person, but due to COVID situation, I guess we have moved to this online mode. So this will be the new reality for the foreseeable future, but I hope all of you are doing well and staying healthy. Before I start, I would like to also convey my regards to Professor Sinha. I think I have recently learned that he has left CSIR after serving there as a director for a long time. So I think he has left CSIR in a very better place. And it is now in the world map of places. I've been trying to work with some of the faculties there and scientists, including Professor Tiwari. So I hope you will see through my talk that there are certain opportunities where we can definitely collaborate. So if you do see something like that, then feel free to reach out to me. We are always open to working with others. All right. So with that, I will start my talk. My talk is titled Optics in the Flatland. I am affiliated with NIST, which is in Washington, D.C. and at University of Maryland in College Park. Okay. So because this is an optics talk, my talk assumes certain familiarity with working with optics. Okay, but I have tried to make it simple enough so that people who are not experts in this field can still understand it. Okay, so where are we? Okay, it's not transitioning anymore for some reason. Okay, here. Okay, so I work at NIST in Washington, D.C. So if White House is here, we are around 40 kilometers from White House and northwest of there in the town called Gaithersburg. The mission of this institute is to promote U.S. innovation and industrial competitiveness by advancing measurement science, technology, and standards in ways to enhance economic security and improve our quality of life. So kind of, if I was going through CSIR's mission statement last night, and it sounds very similar to what we do here at NIST, is to advance measurement science and technology. We have around 3,000 staff members. It is a 600-acre campus, beautiful green campus in the suburbs of DC. And some of the laurels of this institute are we have 5 Nobel laureates that work here. And NIST played a very, very big role, a very important role in redefinition of the new kilogram, which was recently adopted. So now all the fundamental units, as you see here, are based on some fundamental constant. Okay, so now we don't rely on any artifacts, for example, to define any of these standard units, such as second, meter, amps, Kelvin, candela, or mole. All right. So there are a number of labs in this campus, as you see here. And sort of the job of the labs is to conduct research that advances our nation's technology infrastructure that is needed by the industry to improve their products and services. So we are really serving the community here. Okay. All right. So so my lab, which is called the Ultrafast Nano-Optics group. Now the goal of my lab is we study light matter interactions in nanoscale in novel photonic materials, devices, and systems. So we work with new materials. We try to create devices out of them. And finally, we try to integrate these devices into full-fledged systems. Okay. So there are 3 major research areas in my group. We work on this topic of plasmonics, metamaterials, and metasurfaces, where a lot of you are probably familiar with, right? And sort of the goal there is to either spatially, temporally, or spectrally control light. Okay, so I'll give you some examples of this, and this is probably going to be the focus of my talk. There's some background noise, maybe. Okay. Okay, so then, so we try to make lasers, filters, lenses, and pulse shapers out of these. And then when we study these effects in these novel devices, we come across novel phenomena such as, say, the photon drag effect or the quasi-periodicity phenomena. So there's enough interest in our group in just studying these fundamental light matter interactions in these new devices. And then finally, more recently, quantum optics have become hot both in India and as well as in the US. So here we are trying to make quantum systems on a chip. So basically take a lab scale experiment that involves making atomic clocks or atom traps and trying to make them really on a small chip that is manufacturable. Okay. And that is sort of driven through this program at NIST called NIST on a chip. where pretty much every lab experiment that we have going on here, that involves optics is trying to be put on a chip. And I'll show you some examples of this as I go through my talk. Okay. All right, so here's the outline of my talk. I will give you a brief introduction of what I'm going to talk about. Just give you a brief sense of where flat optics or metasurfaces, as they are called, fall in this big picture of optics. And then I'll show you how they work. Okay, I'll go through step by step on how you design them and how you fabricate them and what you measure from them and what are their capabilities. And then in the second half of my talk, I'll talk about devices and systems that are based on these flat optics. Okay. And then before summarizing my results. All right. So if you are familiar with optics, this may be a very, very simple slide for you. But traditionally, when we are talking about optics or controlling light, we are mostly either dealing with bulk optics that you use in your lab and such as lenses, mirrors, prisms, wave plates that you buy from, say, Thor Labs catalog. And the underlying periodicity or the size of these structures, the reason they're called bulk is because the underlying periodicity is much, much larger than the wavelength of light. Okay. Now, over the last maybe 2-3 decades, things slowly moved to smaller dimensions, and then with the advent of what we call micro optics, where now you with nanofabrication and other techniques, people can make things that are wavelength scale, and that's where interest in photonic crystals, spatial light modulators, diffraction gratings sort of came up. And so here the interaction of light is on a wavelength scale. Okay. And only in the last, I guess, 10 to 15 years has things moved to what is called the nano regime, where now we are able, using techniques such as electron beam lithography or focused ion beam milling, we can make structures that are much, much, much smaller than wavelength of light. So here I'm talking about making things that are a few nanometers to tens of nanometers. And that has really expanded this interest or reinvigorated this interest in the field of plasmonics, metamaterials, and metasurfaces. Also, this is the background of this field of photonic integrated circuits or integrated photonics, where now the idea is that you don't need a free space lab setup, but you can pretty much do everything from your lasers to modulators to waveguides to demultiplexers and detectors all on chip. So you do never probably have to go off chip. Okay. And there are remarkable developments in this area on creating sources that are at nanoscale, waveguides, modulators, and whatnot. Okay. And then only in the last, I would say, couple of years, things have, there's been renewed interest in quantum optics, where we are really dealing with atoms or atomic systems on a much, much smaller length scales, such as angstroms. Okay, so here I'm showing you a picture of a chip that is fabricated at IonQ, and you can see this microfabricated chip traps single ions, 32 of them. Each ion here behaves as a single qubit. Right, so this is your qubit, is your bit for your quantum computer, for example. Okay, so you're dealing with individual atoms or ions, and there are of course novel effects that we are aware of, such as tunneling or topology or entanglement that come from working in the quantum regime. And there has been remarkable developments on chip single photon sources and detectors that one could make. Okay, so if you just sort of look at the mile high view of the field of optics, it's no matter if you're dealing with bulk optics or quantum optics, the goal really is to either generate light, manipulate light, or detect light. Okay, so you do this generation through using light emitting diodes or lasers, and you detect light using, let's say, photodetectors. And my talk is going to not focus on generation or detection of light, but mostly on the manipulation of light. Okay, so what do I mean when I say manipulate light? Right, you can do 3 things with manipulation. Okay, so this is again a very simple slide on what I would call manipulating light. I can manipulate light spatially. Okay, so if I shine light on a lens and it focuses, then I'm basically manipulating it spatially. Okay, I've taken a big beam and I've concentrated the light in a very, very small spot. Okay, you can also do this in time domain. So if I have a ultra-fast laser on a nanosecond laser, let's say, or a picosecond laser, let's say the pulse in time looks like this Gaussian here. If I make it go through, let's say, an optic, then I can make this pulse looks weird, okay, or slightly different. And this I would call a temporal manipulation. Turns out that you can log the spatial and temporal degrees of freedom, and do what is called spatiotemporal light shaping, as shown by this sort of cartoon here, where let's say this ball, the size of this ball determines the time axis, if you would. And this pulse is then propagating in space. So what you will see is that if I look at this pulse in space using, let's say, a piece of paper, As you propagate, it will both diffract in time, so this ball becomes bigger, and it will also expand in time because of dispersion in the system. So the pulse becomes longer. Okay. Hey, so this sort of spatio-temporal locking, what it does is not only confines the light in the temporal domain, but it also prevents it from diffracting the spatial domain. So you can generate kind of, using this technique, you can generate kind of novel states of light. Okay. So, okay, so if you're trying to, doesn't matter if you're trying to do spatial temporal or spatial temporal light manipulation, really what you're manipulating is amplitude, phase, or polarization. So let me give you an example, okay? If I take a light beam and I put an aperture here, or an annular aperture, then some of the light will go through, some of the light won't go through, and that I would call an amplitude modulation. If you do this in the time domain, then you're really creating a modulator, okay? If I have light on, and I'm turning it on, off, on, off, on, off, that's my sort of my bit train. And that I would call an amplitude modulation. Light going through a simple lens is a phase manipulation, right? So I've taken this light and I have not delayed it as much, but the light rays that are going through the center of this lens has been delayed quite a bit. So all I have done is put a phase gradient on this flat wavefront that allowed me to focus light. Okay. And then the third degree of freedom is polarization. So I can also manipulate polarization of this spatially varying of this light beam. I can do that also in temporal domain. I'll show you examples of both of these in a second. Okay. And then the goal is either you can do this actively, passively. So such as if I go to Thorlab's catalog and buy a lens, then that lens gives me one function and that's it. It doesn't give me anything else. Okay. So that I would call a passive manipulation, where you make something and you only get one function out of it. Okay. But let's say if you buy a spatial light modulator on a tunable lens, then what you would get is an active manipulation where, oh, now I apply a bias to my system and I can change where this focal point is. Or, hey, I put a new phase function and I can change the shape of the light that is coming out. Okay. Okay, so really what you're trying to manipulate is amplitude, phase, polarization in space or time. And you're either trying to do it actively or passively. The other degree of freedom that one has to worry about when you're trying to accomplish this is wavelength of light. Okay. And what wavelength does is it kind of determines the material choices that one have. Okay. Nice. So if I'm trying to manipulate light at say 400 nanometers or in the UV, we know that silicon won't work. But if I'm trying to do that at 1550, then silicon is a great material for working at 1550. So sort of wavelength, I guess, is very intricately linked to material that you use to perform any of these functions. Okay. All right. So where does flat optics come? So the idea of flat optics or metasurfaces is really what you do is you take your, as an example of a very simple lens, what you do is you take a millimeter scale, let's say a lens that you buy from say Thorlabs, and you are really shoving that function into a very, very small footprint device that is only nanometers thick. Okay. So if I sort of transition through a time period, then lenses have been around for hundreds of years. And then maybe in the last century or so, if you look at the lens very carefully, then there are a lot of parts that are not useful, such as these non-refractive parts. This is just bulk piece of glass. If you remove them, then what you're left with is a Fresnel zone plate shown here. And one could very easily call this a flat optic, right? Like there's nothing wrong with it, but there are certain limitations and issues with flat optics that are based on Fresnel zone plates. And then more recently, people have started making metasurfaces, and my talk will pretty much focus on this. Okay. So let me give you a big picture overview of metasurfaces can do that. Let's say a Fresnel zone plate can do. Okay, a metasurface can provide arbitrary phase, polarization, or amplitude modulation to an optical wavefront. Okay, so it can do all three, and potentially it can also do all three simultaneously. Okay, I'll show you some examples of that. Right. It is a very compact, ultra-thin planar CMOS compatible platform. So you don't need to rely on sort of lens molding techniques. You can go to a fab, photonic foundry, and make these things. So integration of these elements into, say, a CMOS compatible device, such as a photonic integrated circuit, becomes much, much easier. Okay. They offer multifunctional response, meaning you can have multiple functions embedded in a single layer of device. There are achromatic embodiments in literature where you can make them work like a lens, where it doesn't care about color. It functions for all the different wavelengths of light that are incident on it. And the design of such a metasurface, if you would, is not to replace, let's say, a lens, but I call it as application-driven design, which means I have an application in mind where I think metasurface will solve my problem. So I go backwards to design a metasurface that will solve that problem, rather than trying to make a lens that will sort of show up in a Thorlabs catalog that you can buy that will replace sort of this bulk lens. Okay, so I think the difference between sort of a metasurface research at least in this stage, is not trying to replace conventional bulk optics, but trying to make designs that are going to solve your problem. Okay. All right. So this field of sort of metasurface came in prominence after this paper came out in 2014 from Federico Capasso's group, who is a pioneer in this area, on making a metasurface using metallic nano antennas. So what they did at this mid-IR wavelength, 11 microns here, is that they made metallic nano antennas, and each antenna, as you see here, as you go from point A to point B, it imparts a different phase shift when light goes through it. Okay, so what you do is you shine light bounces back and forth, couples to a plasmon mode on this nanoparticle, and then it re-radiates out, and it re-radiates out with a small phase shift. Okay, so if I go from point A to point B, then I have designed an array of these nano antennas that impart different phase shifts varying from 0 to 2 pi. Okay, so if I go from 0 to 2 pi, as shown in this bottom plot here, then all you have done is given this light of a deflection, and therefore light coming out of this metasurface, plane wave incident from the back will come out tilted. Okay, so you can think of this as a nanoscale or optical analog of phase array antennas. Okay, that's all they are. Okay, so what they showed in this paper is that if I look at a bulk silicon or a piece of glass, let's say even, and then you have a normal Snell's law where light goes in, shown by this blue curve, and it bends towards the normal and bends away from the normal. And if it reflects, then it does this. Okay. However, what they showed is that if you make this metasurface, which is sort of ultra thin, hundreds of nanometer layer of nanostructure surface on one end of this substrate, then you can generalize the law of refraction by adding an interfacial phase. Okay, and this interfacial phase can be anything that you design on this layer. And therefore, what the ability that you get is not just traditional reflection or refraction, but you can get anomalous reflection and refraction. Okay, you can pretty much make light go anywhere you want. Okay, because this anomalous phase could be anything. Okay, it's by design. So that sort of revolutionized the field. And at that time, plasmonics was hot, but plasmonics is still very applicable. But at optical frequencies, I think people have realized that if I want to make this device have practical importance, then I cannot work with plasmonics anymore because they are very, very lossy. Okay, and losses are important in certain applications. So things pretty much quickly moved to dielectric metasurfaces. So instead of using metals such as aluminum, gold, or silver, now you have a more larger plethora of materials. Shown 4 examples are here: silicon, gallium nitride, TiO2, or hafnium oxide. So if I use silicon, then I can pretty much work from near IR, so around 800 nanometers, all the way up to terahertz or even microwaves. Okay, so silicon is fantastic for working over a broad range of wavelengths. So if you're trying to make a metasurface that works in the longer wavelength regime, then silicon is your material, and actually is probably the only material of choice that you have. Okay. Moreover, the advantage of silicon is that the fabrication is very, very mature. I can make silicon, pattern silicon in ways that is now foundry processable. Okay. If you now then go to the visible frequency regime, say from 400 or 300 nanometers to 600 or 700 nanometers, then TiO2 or gallium nitride are good materials. Okay. TiO2 has mostly been the workhorse in this area, at least in the last 5-6 years, because of the ability to use atomic layer deposition techniques to make these devices based on TiO2. And so ideally what you want to make is very, very large nanopillars, and you don't want the etching to be too tapered. So TiO2 has been the material of choice because of the ability to make tall nanopillars. Okay. And then similar to TiO2 is another material called hafnium dioxide. It has a higher band gap, around 3.5 or 4 eV. So you can push the operation of these metasurfaces to deep UV wavelength regimes. Okay, this came out in a paper from our group earlier this year. So the advantages of dielectric metasurfaces are reduced optical losses because you're using dielectrics instead of metals. You have more material choices. I've shown you 4 here, but there are gazillion dielectric elements out there. The fabrication procedure is quite standard. It's standard CMOS processable. You do your E-beam lithography or deep UV lithography, and then you etch using standard etching process or die etching or wet etching, be it. And there are a number of applications. Okay. And what you see in this image is that all of these are passive embodiments. Okay, so these are designed to do one function, and they do that function really, really well, but you cannot change that function. Okay. However, there is ongoing work in the community on trying to make them active using either mechanical, thermal, electrical, or optical construction mechanisms. And so there's a lot of work being done such that one can really envision these devices as a nanoscale analog of a spatial light modulator. Okay, and there's a beautiful review paper that came out last year that talks about some of these active transaction mechanisms people are pursuing. Okay. All right, so how do they work? Okay, so now in the next 3 slides or so, I'll show you how, if you were to, let's say, make a metalens, and how would you do it? Okay, so the basic building block in a very simplistic picture of a metasurface is a nanopillar waveguide. Okay, so this is a dielectric high index waveguide on a low index substrate. So if you have a nanopillar like this, a cylindrical nanopillar, and I shine light on it, the light couples into a waveguide mode of this pillar and it comes out. Ideally, you want it to come out without any resonance in there. You just want it to propagate through it. So of course, if you're going through a high index material in a low index background, then light gets delayed. So naturally, if I change the diameter of this nanopillar shown by these pillars here, going from 70 nanometers say to 275 nanometers, or when I am at a 70 nanometer limit, then you can see that less of my light is in the nanopillar, more of it is outside the nanopillar. But if I go to 275 nanometers, almost all of my light is inside the nanopillar. The mode is pretty much confined within. So you would naturally expect that when the light propagates through this nanopillar, it will come out faster. Whereas when it comes through this nanopillar, it will come out slower. So by having a library of these nanopillars, you can really engineer your system such that you have 0 to 2 pi phase shift. Okay. So I can look at it a little bit more mathematically. So here is my nanopillar. Instead of circular cross section, I'm showing you a rectangular cross section. And I change its side length here from, let's say, 70 nanometers to 150 nanometers. And what you see is that indeed you get a 0 to 2 pi phase shift. And as I mentioned, you don't want transmission to be too different. Okay, so transmission should stay at 1 if you're trying to make only a phase only metasurface, but you can get a 0 to 2 pi phase shift. Okay. Notice very important thing here are if you keep changing the diameter or the width of this nanopillar, that at one location you hit a resonance, you see a big transmission dip. Okay, so this resonance is inherent resonance of this nanopillar that comes from a geometric near resonance. And so basically what happens is that in that size scale for that wavelength, light is trapped inside the nanopillar. Okay, so let's say if you're trying to make a sensor or a nonlinear resonator or trying to enhance nonlinearity, then you ideally want to work with this resonance. Okay, so this is not a bad thing if you are trying to use resonance to enhance certain phenomena or to try to do sensing or something with it. Okay? But if you're trying to only make a lens, then you don't want this resonance. You want to stay away from it. And so you work in this regime. Okay. All right. So now I have a library of nanopillars that can give me 0 to 2 pi phase shift. Let's say I want to make a lens. My lensing function is this, shown by this hyperbola or a spherical phase function. So I have a plane wavefront and I want this wavefront. So if I now take this wavefront and I say, okay, how much phase shift do I need? I can plot that in an x to phase plot and unwrap 0 to 2 pi. Okay, so it's shown here. So if you do this phase unwrapping, then this is the phase that you need for your meta lens or this surface to behave as a lens. All I have to do now, as you can simply see, is that, oh, at this location, I want 6 pi phase shift. I will take this nanopillar, put it here. Oh, at this location, I don't want any phase shift. I will take a 70 nanometer pillar and put it here. And you basically repeat that. Okay. And so this is 1D. If you rotate this around the axis of your lens, then you have a complete 2D lens. And so that's basically what is involved in trying to, let's say, make a meta lens, is to spatially place these nanopillars at specific locations to give you the desired phase shift. Okay. How do we make them? We have certain different processes for different materials. Shown here is the process for silicon, where we use electron beam lithography to pattern a hard mask made of aluminum. Actually, more recently, it's aluminum dioxide. And then we use a cryo etching technique based on fluorine chemistry to etch through the nanopillars. And finally, we remove the hard mask. So shown here are some SEM images, and you can see in the bottommost SEM image, this 0 to 2 pi phase wrap. I have a 0 phase shift for a small nanopillar, and as I'm going towards another region, then I have a larger nanopillar that is giving me a larger phase shift. So this sort of clearly shows the 0 to 2 pi phase wrap as you go from along this nanopillar radial direction. Okay, so the trick is basically to create a device that looks like this if you're trying to make a lens. Okay. So then you can measure the functionality. So once you have made it, this is how it looks like. But to bare eye, this is a glass slide, and these midges or these sort of marks that you see are the meta lenses. They are really few hundred nanometers thick. Okay, they don't look like much. And if you zoom in, then what you see are these nanopillars. This particular image is for, instead of a square nanopillar, this nanopillar has a rectangular cross section. Okay, and the reason we did that is because for two orthogonal axes of this nanopillar, I can impart two different phases. Okay, so you don't have to work with one wavelength; you can work with two different wavelengths. Okay, for two orthogonal. That's what's kind of the idea here. And so now if I shine light at these two wavelengths, this is a Metalens that was designed to have a numerical aperture of 0.9. So really, really high numerical aperture. I can focus light to its diffraction limited spot size. Okay. So the advantages of Metasurfaces is that it can give you the ability to polarization multiplex using, let's say, an oddly shaped nanopillar. But the disadvantage is that with a single layer metasurface that is shown here with a very, very high numerical aperture, it has a very large chromatic aberration, which means that this Metalens works fantastic for these two wavelengths, or let's say one wavelength, but it is terrible at any other wavelengths. Also, it has a very small field of view. What that means is that it works great if I have light normally incident on the metasurface, but if my angle of incidence is slightly larger, then my spot size looks very aberrated. Okay, there are ways of correcting all of this, chromatic aberration and field of view, by using, say, a doublet or a more advanced design of the metasurface. Okay, so what I'm showing you is a very, very simple design that uses rectangular or square nanopillars, and therefore there are certain limitations that come with it. But if your goal is to work with normally incident light and to focus light at a very, very small spot size with a very high numerical aperture in a very small compact footprint, then this is the way to go. All right. I told you about materials. So here is again our library of materials that we work with here at NIST in my group. So we work with silicon and for any wavelengths above around 650 to 700 nanometers, or all the way up to terahertz. Okay. There's a new material we work with, which is tantalum pentoxide. Its band gap is around 300 nanometers, and it has an etching chemistry that is very similar to silicon. And then for deep UV and UV visible regime, we also have atomic layer deposition based fabrication approach that we use to make metasurfaces based on TiO2 or hafnium dioxide. Okay. Hi. So what are the functions you can do? I showed you a simple lens. You can make a hologram just by imparting a different phase front. You can create a hologram that shows up. You can create arbitrary beams such as an accelerating or airy beam shown here. One other advantage that sort of function that wasn't probably very clear is that when you're working in a linear basis with, let's say, a rectangular cross-section pillar, then you can have two phase functions for orthogonal polarizations. If I go to the circular basis, then the same principle holds, where by using a different embodiment of a nanopillar here for two different right or left circularly polarized light, I can have two different phase functions as well. Okay, so it works equivalently for linear and circular polarization. So you can create, let's say, a one particular hologram for one circularly polarized light, and when you flip the handedness, you see something else. Okay, so it really gives you functionality to have two different phase functions. Okay. And so this is the design concept that I talked about, because this is very, very simple to understand. It is just a nanopillar where you change the size and you get a different phase out. And it turns out you can design this nanopillar such that at the phase along two orthogonal axis is pi over 2 out of phase. And when that happens, this nanopillar now acts as a nanoscale quarter wave plate. So imagine now if I have a light incident on this, and if I orient the nanopillar correctly, then I can get circularly polarized light out. If I do the same thing and instead choose a pi phase shift between the two orthogonal axes, then I get a half wave plate operation. Okay, so then I can rotate my polarization. So you can play with not just phase, but you can also play with polarization and both linear and circular. Okay, there's another embodiment of this metasurface that is slightly more complicated to understand, which is based on what is called the Pancharatnam Berry phase or geometric phase, and that embodiment uses circularly polarized incident light. And what happens is that if you have a particular handedness light that is incident on this PB phase metasurface, as they are called, then what you get is light out with opposite handedness. So if I have right incident, then I get left out, left incident, then I get right out. Right? But I can have two different phase functions imparted on this metasurface. Okay. And what is the advantage of a PB phase approach over a normal propagation phase approach? The advantage is that in a PB phase condition, the phase difference that you get upon propagation through the nanopillar is determined by the rotation of this nanopillar, not by its size. So when I'm trying to get different phase functions for this device based on this concept, then I have to make different size nanopillars. Whereas when I am trying to get the same function with a PB phase metasurface, I want to make one nanopillar of one particular dimension, but only have different rotations spatially. Okay. And that's just based on the concept of this PB phase, where the nano pillar is designed as a half-wave plate, and if you go through a half-wave plate, then and you rotate it differently, then what you get is a phase shift that is dependent on its rotation. Okay. So now I can summarize all of this as building blocks and a very simplistic picture. Okay. Let's say if my goal is to make a device that can only give me phase, so let's say a lens, then I would either work with a rectangular or a square cross-section nanopillar. Okay. But I can, if I take this rectangular cross-section on an elliptical cross-section nanopillar with two different phase functions across its orthogonal axis, and I set it such that I can get a quarter wave plate or a half wave plate condition, then for a linearly polarized light, I can get circularly polarized light out, or I can get a linearly polarized light out with a different phase function and also rotate polarization. So I can control ellipticity and phase. I can control polarization in phase, depending on how I design this in a metasurface. If you have worked in an optics lab before and you're trying to make an amplitude modulator, then what you do is you take a half wave plate and you put a polarizer in the back. Okay. So if I have a half wave plate and a polarizer, then I get amplitude modulation. That is simply shown by this picture here. We can, it turns out, make it in an integrated way where we make nanopillar on one side and we make a polarizer on the back side in a single device. And then this concept of geometric or PV phase is where you make a nanopillar with two orthogonal axes, again with acting as a half wave plate, but instead of linearly polarized light as input on it, you have a circularly polarized light input. And if you have circularly polarized light out, then what you get is the opposite handedness with a phase shift. Okay, so this is the library of sort of a very simplistic design nanopillars that will give you the function that you want. The other thing I talked about is wavelength. So let's say a nanopillar that has circular or square cross section will only give you ability to control one wavelength. If you have two orthogonal axes, then you can control in principle two wavelengths, but that's about it. Okay. How about if you're trying to make a lens that is achromatic? So you need more design freedom, basically, right? Just having this ability to change the width or the height of the nanopillar is not good enough. Okay. So shown here is what is required if you're trying to make an achromatic metasurface. Yes, and there you stop worrying about just the phase itself at certain frequency. You have to of course worry about it, but what you really worry about is group delay, dispersion, and group delay. Okay. So what basically that means is if I have number of different colors incident on a metasurface, yes, then I want the whole wave packet or the whole group of these wavelengths to reach my focal point at the same time. So naturally, as you can see, I want to slow this wave packet down and I want to fasten this one, and so that they meet coherently at this focal spot. Okay. So to achieve this, again, you make a library of nano elements that will give you this function and to control this group delay. And shown here are three papers, very recent, from Kapasso's group and Anpang Yu's group, where they make library of nano pillars shown here that can achieve this function and give you achromatic operation over a large frequency range shown here for this paper. Okay. Hey, so what is different? The only difference from what I showed you before and versus what is here is design freedom. And look here, I have only if my thickness of silicon film is fixed, then the only thing I can change is its width. Okay. Whereas here, if my thickness is fixed, then I have 5 free parameters: width and length of a nanopillar, and the spacing between them. If I go to a more complex design with 3 nanopillars, then I have 10 design freedom. So basically, you have more free parameters that you're working with. So therefore, you have an enhanced library that can allow you to achieve this function, and such that all the wave packets come to the same point. Okay, but this is talking about metasurfaces to, let's say, focus light. But metasurfaces can do a lot more. Or I showed you examples of making a lens, controlling polarization or multiplexing polarization, and it can also generate non-Gaussian beams such as Bessel area and vector beams. Depending on the phase you put, you can make holograms. But what is really amazing is that some of the materials that one used to make these metasurfaces are called have nonlinearities in them. And so since these are nonlinear metasurfaces, as not only can you shape the fundamental beam, let's say focus light at the design wavelength, but you can actually, turns out, design the structure so that you have a very high nonlinearity, but the nonlinear beam that comes out is shaped. Okay. And then finally, there has been revolution in this field of what is called machine learning or topological optimization or inverse design, recently, where now rather than making a metasurface out of, say, a pillar library such as this, you don't worry about any of that, but you define your function. And shown here as an example is that, let's say I want my light to deflect at 75 degrees and I want it to do it really, really well. Then maybe I cannot achieve that function using the design library I just showed you. So the way one would do it is then you design this function that you want the metasurface to do, and you run an optimization algorithm using commercial softwares or your own codes, and it will spit out a design that will look very non-ideal. So see here, there's no way one could make a library for a design like this, but this particular metasurface then acts as a beam deflector, that deflects light from 1 micron wavelength at 75 degrees with the efficiency of around 100%. Okay, so you can make, this is kind of what I meant when I was talking about in my introductory slide, is that the design is sort of application driven. So you design your metasurface to satisfy a particular problem that you're trying to solve, rather than try to make a generic lens, which is already pretty good to begin with. All right, so this is kind of my very, very long introduction of flat optics and how we use them to shape light. Okay, so now in the second half of my talk, I'm going to give you some examples of devices and systems that we are working with here at NIST in my group that are based on these flat optics. Okay, so one of the things that we are doing is trying to make an atom trap in a let's say a physics lab based on rubidium and strontium eventually, and the goal is that if you can trap atoms, then you make a clock out of it, and that's the basis of the clock that is currently out there in the world that we define our time out of. Okay. Based on cesium atoms. So here is an example. So if you take a rubidium atom cloud in a 2D MOT, magneto-optical trap, and you translate it and bring it to this lattice configuration where there's a lens here, another lens, you retroreflect it, you get a standing wave, then you can trap an ensemble of atoms shown here. Okay, so what we have done is now started individually replacing components in this system, a very complex optical system, with metasurface based components. And so one of the first ones we did was to remove this lens here and replace it with a Metalens. And what you see is that, yes, indeed, by replacing conventional optics, Metalens is not doing anything untowards to the atoms. Okay, so one can look at it more quantitatively. So if I look at the fluorescence as a function of time, what you see is that at a conventional optic fluorescence versus lifetime is shown here in orange versus the Metalens, and they behave very, very similar. Okay, so there's nothing a Metalens is fundamentally doing to the atoms, such as heating them or scattering light such that they leave the trap. So they work correctly, and you can look at it more carefully where you modulate the trap, and then you can look at the radial and the axial trap frequencies, and again you see dips at the correct frequencies. So sort of all of this, what is showing you is that Metalens seems like a viable approach to replace conventional optics if you're trying to compact your system down. Okay. A more difficult experiment, which is where we are headed right now, is to make single atoms. Okay, so then single atoms can then act as your qubits basically for a quantum computer or whatnot that you are trying to make out. Okay, so here is again an image shown with a much higher NA Metalens that is mounted directly inside the science cell. So this Metalens is a 0.9 numerical aperture Metalens with a focal length of 500 microns that is mounted inside the science cell that will have eventually rubidium vapors. So we bring the MOT close to the metasurface, and as you can see that the metasurface is not doing anything untowards to the atom. And then if you use a Metalens with a longer focal length, then you can more clearly see that indeed the Metalens can trap an ensemble of atoms at this focal spot, okay, by looking at the fluorescence from the atom, okay. So the idea here is that now we are trying to use this Metalens to trap single atoms, which is a much stronger, harder experiment. And so if you can trap single atom, then you can start doing quantum optical experiments with those atoms, okay. So that's kind of the idea. But you can see that a typical 0.9 NA objective that you buy from, say, Thor Labs or Advent Optics or whatever catalog you have it, are big, bulky, whereas this metasurface is only hundreds of nanometer thick and few millimeters in diameter, and it's able to do the function really well. Okay. All right, so why am I talking about all of this? My talk is about flat optics. So I've given you some examples of replacing flat optics in a very simple optical setup and the functionalities it can achieve. But ideally, what you would want is to replace this whole system, okay, with integrated photonics, where everything is now on a chip. And this is kind of where the program NIST on a chip comes. And this is where people are trying to make things basically on a chip. So just to give you a brief summary, there has been a revolution in the last 5 years or so, or 10 years, in what are called photonic integrated circuits. And there have been two enablers for it, I call it. One is silicon photonics, so ability to pattern silicon such that you can propagate light on chip quite far. And then the second is heterogeneous integration. So silicon is a good material to, let's say, absorb light, but it is a terrible material at emitting light. But hey, why not put gallium arsenide on the same platform as silicon? So now I can have an emitter, detector, and a waveguide and a modulator and what have you on the same chip, as sort of envisioned in this cartoon here. And so what has happened in the last, I guess, 5-6 years is that a plethora of companies, some of them are listed here, have come up, and now you can really start thinking about photonics from an electronics design point, where you can use softwares listed here to make your photonic integrated circuit design. You can send your design to a photonic foundry. They will create your device that can be cut into small chips, and it will do the function that you want. Okay. So what you notice here is that because of the need for more and more data in data centers and whatnot, and people have started transitioning towards sort of completely optics based systems. Okay, so why am I showing this? The reason I'm showing this is that for, let's say, if your goal is only to generate light, modulate it, and then transmit it, and while never leaving the chip, then this is a fine platform. Okay, but there are a number of applications, including some that people at CSI are working on that require you to leave the chip. Light has to come out of the chip, and some of the applications are, let's say, when you're trying to do biosensing. Okay, so if I have a biomolecule that I'm trying to sense, then I cannot leave my light inside the waveguide. I have to come out of it. Okay, similar with talking about atomic systems. Okay, I showed you examples of this trap with number of atoms or ions trapped. And again, if I'm trying to do atomic spectroscopy, then I cannot keep my light in the chip. I have to come out of the chip, talk to the atom, and go back in, let's say. Right. So that therein comes a problem where light matter, there are a lot of problems where you're trying to talk to the outside world that requires light matter interaction in volume rather than in surfaces. Okay. So basically what that means is my light is in a waveguide is confined to a dimensions of hundreds of nanometer, or let's say a micron, whereas talking to systems such as biological or atomic systems, or even trying to create a trap, you need beams that are millimeters such a free space. So how does one come up with a system like an integrated photonic platform where you can basically have your optics lab on a chip, but then only come out of the chip where you need to be to talk to your system and go back in, if you would, with very well controlled phase, intensity, and polarization. So how does one create a platform? And I'll show you an example of that in a second. And so here is a proposal that was published in 2 papers, back-to-back papers from Vladimir Akshi's group together with my group, where what they showed was, okay, let's say my light on a waveguide shown by this sort of line on the here is hundreds of nanometer, and I want a bigger beam out of it. Then what you do is you create what is called an extreme photonic mode converter, as shown in this paper, where you adiabatically bring this waveguide closer to the slab mode and leak light into this. So what that does, it does a 1D expansion of the beam. And then when this expanded beam hits a grating, then when light comes out, then what you have is a free space beam that is hundreds of microns. So notice what this has done. You can use integrated photonics to propagate your light, but whenever you have to come off the chip, you use this extreme mode converter that will give you a beam hundreds of microns. Okay. And then, but notice that what you can get out from this apatized grating is a linearly polarized light. That is hundreds of microns in diameter with sub-control over its directionality. It doesn't give you complete control over directionality, divergence, and polarization. So directionality means what a mirror would do. Okay, divergence means what a lens would do, and polarization is what a wave plate would do. Okay, so ideally what you want is complete control over all 3 using an integrated platform. And that was proposed in this paper here, where we said, okay, yeah, why not we put a metasurface on top of it? And now metasurface, as I've shown you, can do all 3 very well. So now I can have light and my waveguide propagating this chip. And whenever I want to talk to someone on the outside world, then I come off the chip with very, very well controlled divergence, directionality, and polarization. Okay, using a single layer metasurface. All right. So the reason we got into this project, we are not just doing it because of the heck of it. We were trying to do this because we have a big program here on atomic clocks. So some of you might not be familiar with what chip scale atomic clocks are. So I wanted to spend maybe next 5 minutes talking about atomic clocks, what they are, how they work, and then show you where we are applying these concepts to. Okay. Right. So if you look at a simplified energy diagram of, let's say, an atomic system, then you have these hyperfine energy levels that are separated by microwaves or RF frequencies in the gigahertz regime. And then you have these optical transitions that are much, much larger. Okay. So if you're trying to make a clock out of, let's say, an optical transition, then it's fantastic, but there's no mark. They work the best. I'll show you in a second. You use lasers, you use electrical dipole transitions, but there are no commercial products. Okay, so all of the clock R&D activity in the US currently or in the world is based on optical clocks. Okay, the microwave clocks are fantastic. They work great. Okay? They are based on a quartz crystal oscillator that oscillates at, let's say, 10 megahertz or so. Oh, and then it's for frequency multiplied to 10 gigahertz. And so pretty much any commercial clock that you see out there today is based on this microwave transition. Okay, so what is the issue? The issue is sort of fundamental. If you look at a microwave clock, then it has a microwave synthesizer that probes this hyperfine transition in an atomic system. And then you try to lock to that atomic transition and using a quartz crystal oscillator. And once this is locked, then you get an output that is basically your RF frequency that you can use for your application. Okay. So there are a couple of companies that make these things, including Teledyne and Microsemi. So these guys sell around 20,000 of these units every year. It's a very, very big market. So if I open this matchbox size piece, is what this is basically is a chip scale atomic clock that is giving a user output out at 10 megahertz or so, or maybe 10 gigahertz. But its stability of this clock is limited to around 10 to the minus 13 at 1 second. Okay. Another thing that you will notice is that when you open this clock, there is a small physics package in there. And if you look more closely, this physics package is tiny. It has a Wick cell, a wave plate, and a rubidium vapor cell where you go through light and a photodetector. Okay, so this looks like a very simple optics experiment here, right? You take light, linearly polarized, convert it to circularly polarized. You do atomic transition spectroscopy or absorption spectroscopy, then you detect your light. Okay, this tiny thing, right? So, but the issue is that this device works at microwave frequencies where your inherent stability is limited to 10 to the minus 13 second. Okay. If I now go to optical clocks, instead of it looks very similar. Instead of a local oscillator that is a quartz crystal oscillator, I use a laser and I lock it and I do down frequency conversion using a frequency comb. Then I can again get an RF output, but my physics is based on optics. Okay, and notice that if you are looking at the Allen deviation of this or the stability of this clock, then it is inversely proportional to Q, and Q is directly proportional to the frequency of operation. So naturally, if I go from microwave frequencies to optical frequency, then I get a 10,000 times higher sensitivity or a Q quality factor. And its stability is better because lasers are better. There's less environmental susceptibility because I'm not working with microwaves or electronics anymore. And so in all, this is a better package. And that's why if you look at the frequency stability of, let's say, optical clocks over time, then what you would notice is that while microwave clocks have slowly become better, optical clocks are just fundamentally way or orders of magnitude better than microwave clocks are. Okay. So why am I talking about this? Is I've shown you two examples of a commercial microwave clock, and then two other examples are shown here. And what you see is that the stability of these microwave clocks are in the 10 to the minus 11 to the minus 12 regime, whereas as these bigger clocks with much, I guess, fancy electronics and optics and whatnot, you have it, can give you 2 orders of magnitude better stability. Okay. But when you go to an optical atomic clock, this is how they look like. This is the Gila atomic clock in Boulder based on strontium atoms, and this is how the lab looks like. This is how the lab looked like 20 years ago. This is how the lab looks like today. Okay, there hasn't been any improvement in trying to miniaturize optical atomic clocks. Okay, there was one effort in Europe, because ideally what you want is, if you have an atomic clock, you want to take it to places and then do measurements locally using the clock. So there was an effort in Europe in trying to make this clock directly on a tractor trailer shown here. And again, if you go inside the trailer, this is how it looks like. Okay, and these clocks basically give you slightly better stabilities. And there are a couple of other examples of this. Okay, so the idea through all of these sort of evolution of microwave atomic clocks to optical clocks and trying to make a portable atomic clock, they all come from programs run by DARPA, where what they're trying to do is, what they're trying to do is trying to reduce the swap, which is size, weight, and power of an atomic clock. And they are trying to improve the efficiency. So if I look at the Allen deviation as a function of size, then naturally when you make a very, very large atomic clock, then they give you better performance, but they take up a lot of space, like that tractor trailer. Okay, so how about, is there a way where you can go diagonally along this direction, where you make small and you make better clocks. That's sort of run by DARPA through these programs called ACES and currently A5. We are trying to make a chip scale atomic clock. And why would one want to do this? Is so the stability of atomic clocks as going down here determines a lot of strategic areas. So let's say if I have a low swap clock, such as the ones I showed you before, the two matchbox size ones, then they're really ideal for navigation and undersea exploration. Okay. But if you try to make this more field deployable clocks, such as the one shown here in this plot, then they are better for tactical applications such as telecom, finance, military, and communications. And then the really, really good clocks shown here by this blue plot are very, very good for interferometer, gyroscopes, radar, metrology, navigation, and fundamental physics applications. So sort of the idea is that basically, can you make clocks better and make them small such that they are field deployable, they are manufacturable, you can take them places and address all of these very, very important application areas, which is a very, very big market, like $1 billion market. Okay, so through this program with DARPA called PROCUS, Photonic Optical Clocks using Ultracold Strontium, the idea is to take this Strontium clock shown here with a stability in the 10 to the minus 14th regime and transition it to a coffee cup size device is with similar performance. Okay, 10 to the minus 14 square root of 4. Okay, so if you see, it's a remarkable change. Of course, what I'm not showing you here is that in this particular program, the lasers are allowed to be off chip. However, there's a parallel program running with DARPA where they're trying to make all the lasers on chip for this particular application. Okay, so maybe in the next 5 years or so, we will start seeing systems where lasers and your optics and everything is integrated in a single box. Okay, so again, the heart of all of these atomic clocks, as I showed you before, is the physics package where you're trying to use lasers and light to trap atoms. That's where I work. And so here I'll show you example of how we are trying to use metasurfaces. So if I take this box and I open it, then there are a number of components such as on-chip frequency combs that are working at different frequencies, on-chip lasers, on-chip second harmonic generators, on-chip reference cavities. But the heart of the package is this 1 inch by 1 inch by 1 inch cell here, which will be shown in this picture better here. So this is a 1 inch by 1 inch photonic integrated circuit that is a metasurface on top of it that does beam expansion, beam reflection. And then the idea is at the center of this, we will trap strontium atoms. So of course, there are a number of requirements for you to trap atoms. They just don't trap by themselves. So you need certain wavelengths, you need certain powers, you need certain radius, you need certain polarization. So what I'm going to show you examples is that if I am trying to trap strontium atoms with very, very, very carefully designed and geometries of metasurfaces, we could address this channel in a very compact package. So this is a 1 inch by 1 inch by 1 inch package where we think we can trap atoms. Okay, and that is currently ongoing. So here is how the PIC will look like. So this is all these the lines are all these waveguides that will take light to this extreme mode converter shown by these rectangles here. And right on top of this, we will have a metasurface plate. And that metasurface plate is going to direct light to different directions and then eventually trap atoms. Okay. So here is an example of what the metasurface will look like. So let's say for this program, I want to make a metasurface that does this function. So a single metasurface changes the angle, divergence, and polarization. So imagine a metasurface layer that is doing 3 functions, that of a mirror, a lens, and a wave plate, okay, at this particular wavelength. So we have design requirements. So I'll show you an example of this in my next slide. I think I'm running out of time, so I'll go quickly. So what you see here is a metasurface that we made for operation at 461 nanometers to probe the strontium transitions or trap strontium atoms. And what you see is that this rectangle is the metasurface. Okay, if I shine light from the back side, it is a linearly polarized light, but what comes out is equal TE and TM, which means I have converted my light to equal basically circular polarization. And then the second thing functionality I want is to change the tilt, which we have measured. I can show you here easily. Okay? And the third functionality that we want is to diverge the light. I told you, you have hundreds of microns beam from a PIC, but I need millimeter size beams while talking to the atoms. So you need to diverge it. So this movie will, if it works, will show you, it doesn't work. It's basically what it shows is that if I do a Z-stack image, then you see a diverging beam coming out of this PIC. Okay, so pretty much a single layer of metasurface is doing all 3 functions and to try to accomplish that goal. A very interesting metasurface that we also need for this program is what is called an anomalous reflector. So here what you do is you take this diverging beam coming from the bottom side and you reflect it at this weird angle. So notice the reflection. The reflection has to maintain circular polarization. It has to collimate the beam. So it's doing a function of a curved mirror. and it has to deflect light at this odd 45-degree angle. So it is doing this anomalous reflection. So think of this as a flat surface that's doing a 45-degree reflection. Okay. So if I now use, we have made these devices, of course, and you can see that when I have diverging light hitting this metasurface sitting here, then what you see is when the light hits this guy, then you see a bright spot at 45 degrees. And we have now also measured the efficiencies and polarization and whatnot for this beam, reflected beam, and it sort of works. So again, in metasurfaces, I don't see either for this metasurface or for this metasurface, I don't see, there's no free space equivalent that can do this function, period. Okay. Hey, so one of the issues that we ran into that I'll talk about briefly, just to give you a perspective, is that a lot goes into the design of these metasurfaces. So the efficiency here is around 40%. But more lately, we have been playing with what is called inverse design to try to come up with non-arbitrary looking, I guess, trivial looking designs of metasurfaces that can give you much higher efficiencies. So here is shown an example of a metasurface designed using inverse design, in where we set the goal that the metasurface should do this reflection and do it really well. I don't care how the pattern looks like, how the shapes look like, if you would. And noticeably, you can see that the efficiency went from 40% to 80%. So this is kind of the power of inverse design. So how that works is basically what you do is you run this is what is called a joint-based simulation using a gradient descent algorithm. So you have light incident on the metasurface or whatever your device is going to be, and you basically define a figure of merit. And the figure of merit in this case was I want to diffract light at a certain angle, and I want to have most of my power in that diffracted order. And so what you do is you run a forward simulation and a backward simulation, and then you create the gradient of that. And the goal is now to maximize or minimize this gradient, I guess. Yes. Okay. So this sort of adjoint-based simulation is very elegantly shown in these two papers in more detail. But once you run it, right, after sort of, let's say 200 or 300 iterations, the simulation reaches a steady state, and it basically spits out a design that looks like this. And what basically this is saying is that, hey, look, for both TE and TM polarization, and you can have a 90% efficiency and deflect light at 45 degrees. Okay, and the simulated efficiencies were around 90%. So you can see that just for the function that I need, which is to deflect light at 45 degrees, this metasurface does a fantastic job. Okay, but it does not look trivial, or I cannot directly design it, right, and then achieve that functionality. I have to do the inverse approach. There are a number of other examples of this. One of the leaders in this group is Jelena Vukovic's group at Stanford that have made free softwares available for students. And then there are other groups out there that work in this, where you can solve a lot of functional requirements in your device by going to this approach where you define what the problem is, and then you figure out what the solution is. And the solution may not look normal to your eye, if you would, or sort of it wouldn't make sense, but it does the job. Okay. All right. So in the last maybe 5 minutes or so, I will talk about one more project that we have where we shape ultrafast pulses using metasurfaces. And so maybe here I'll maybe quickly skip through it, but the idea is sort of doing temporal manipulation. I've talked about spatial manipulation, and where you can shape light in space using lens or wave plates or mirrors. Here I'm talking about shaping light in time, where you take a Gaussian pulse and you try to make it go through a pulse shaper, again do this transformation, and you get a shape light out. The reason I want to talk about this is because this field of ultrafast optics has been fantastic over the last 30 years. It has won a number of Nobel Prizes, including the more recent Nobel Prize in Physics given to Donna Strickland. And really what they did was they took an ultrafast pulse and they made it propagate through an optical fiber and made it chirped meaning longer in time, which basically means making it go through a material that has a positive dispersion, okay, such as glass. Okay, it has won Nobel Prizes in nonlinear optics. It has won prizes in femtochemistry. So a number of different applications require one to shape light. And so we have been working on this area again using metasurfaces. As the sort of the tricky part with working with femtosecond pulses is that they are inherently broadband. If I have a pulse that is, let's say, very, very small, 7 femtoseconds, then its bandwidth is around 200 nanometers. So naturally now I'm no longer working with a single wavelength, but I'm working with hundreds of sort of comb lines, if you would, or thousands of comb lines. And now the goal is try to address each comb line and that constitute this ultrafast pulse to give you the shape pulse back, basically. All right, so shown here is that what you do is you take this pulse, you spectrally disperse it, so you separate all its colors, then you address individual colors using a metasurface, and then you combine the pulse back, and what you get is your pulse with the desired functionality, with the metasurface imparting their phase function. Here's an example of what metasurface looks like. If you zoom in into one of these, you will have this. Each line here is a metasurface with 25 million nanopillars. So this is a lot of lithography, and then we are able to shape light. More recently, we have been working on a project where we can not only shape phase and amplitude properties of these ultra-fast pulse, but we can create pulses that look like this. So what you are noticing here is a pulse that is only, let's say, 200 femtoseconds, but the leading edge of this pulse is right circularly polarized, and right at time t0, it changes handedness and becomes left circularly polarized. So crazy things like this one can do with using metasurfaces, where you can generate pulses as where in Poincare sphere, let's say this axis, this point here in the Poincare sphere is right circular polarization, and the bottom one is left circular. Then you can make light take arbitrary paths through this Poincare sphere, on the surface of this Poincare sphere. Okay, so you can create non-arbitrary light fields. So with that, I will conclude. I hope I have shown you that metasurfaces offer a very compact manufacturable platform for shaping light, both in time domain and spatial domains. And it has presents opportunities in a number of fields, including atomic physics, integrated photonics, and ultrafast optics, and among others. And there are new advancements that leverage developments in inverse design and machine learning to give you sort of non-arbitrary designs that give you very, very good functionalities. So you can shape light in space, you can shape light in time. A paper from our group came out last year in Science on this sort of temporal shaping thing. And with that, I would like to thank you. This is my group. Wengshi is a senior research scientist, and we have 4 postdocs. This is not a educational institute, so we don't give degrees, so we don't have students, unfortunately. But we work with postdocs, and then we have collaborators, and our funding comes from Army Research Lab, NIST, and DARPA. My email is listed here, so if I don't have time to answer your questions, feel free to send me an email, and I will be happy to answer them over email. With that, I would like to thank all of you for your attention, and be happy to answer any questions that you may have. So are there any questions?
Hello.
Keshav, is there any question? I think there are 2 questions in the chat box. And first
Okay.
question is, can we send data through the light by any means, like laser?
Yes.
Okay. And the second question is, what are the prime factors that affect sensitivity and quality factor?
So the quality factor is basically your center wavelength divided by the line width of your resonance. Center wavelength is your operation wavelength. So your line width basically then determines your quality factor, and line width is basically determined by the loss of your material. Okay. So if I have, but let's say I'm working with silicon at 1550, then it's basically lossless. I can make a resonator with very, very high Qs that people have shown, where you can make quality factors on the order of like 1 million. But if I take the same resonator and scale it down to operation at visible frequencies, then my quality factors are much, much smaller, right? And then, so sensitivity then is inversely proportional to now your quality factor. So if you want very, very sensitive, then you want a very high quality factor. And so I guess the primary factor that determines sensitivity and quality factor, which are both interlinked, is the loss in your material.
I think there are no more questions, but I want to ask one question, that how we can compare conventional optics with the optics made using metamaterials, like from future perspective.
Okay, so I think the traditional optics is not going anywhere. They work well. They are cheap. They are manufacturable. People make them, and they work fantastic. Okay, so I think where metasurfaces see as an application is where you have a particular application in mind, right, which is compact, and you need a particular functionality, and that could be your cell phone camera, right? So there's a lens. If you take an iPhone, there's a lens in the back of it that sticks out of it. Okay, that's just ugly and gaudy and big, and nobody wants that thing sticking out from the back. So in principle, one can replace that with a metasurface and shrink the footprint down for that camera, for example, right? So there are certain very specific applications where metasurfaces can do make an impact. I know companies. There are 10 companies working on this area of metasurfaces and trying to bring commercial products out to the market.
Okay, thank you. Keshav, please take this session.
Okay, sir, I have a question. In one of your slides, you showed that from axis to sides of the lenses, there is a phase shift and light converges to a 1 point. So through metal lenses, can we get this much range of phase shift, phase velocity?
Okay. Right. So the phase depth typically that you need is 0 to 2 pi, right? Because after that, the phase wraps itself, right? So ideally what you need is a phase depth of 2 pi, and pretty much with materials that I showed you, TiO2, tantalum, silicon, or gallium nitride, you can get the phase depth, right? So if I'm say like trying to tilt light at very large angle, then I need a very large phase depth, right? It's a very quick phase gradient, and so I think the limitation is not whether you can get the phase depth. The limitation is how many nanopillars can you make close to each other, right? So if I'm trying to tilt light at a very large angle, then I need a lot of nanopillars in a very small area, and then it comes down to your lithography limits, not whether you can get the phase depth or not, right? And that is kind of the issue with Fresnel zone plates is you get the shadowing effect because of this curved surface, right?
One more question. Sir, you showed the pillars which are 90-degree straight. So
right.
Through lithography, can we get that kind of accuracy?
Through lithography, it's kind of hard, but I will show you one slide. If I could open this again, and the approach that I sort of didn't talk about is so silicon etching is actually pretty well known. Okay, so when you look at nanopillars that we make for these programs, you can see they look pretty straight. Okay, they don't have much taper to them. This is because silicon etching can be done really well. What I wanted to show you is the TiO2 and the other metasurfaces are not made by etching. Okay, they are made by this process called damascene. Okay, so here what you do is you do your nanopits in an electron beam using electron beam lithography, but you make pillars using atomic layer deposition. So you backfill these voids with ALD, then you do argon ion milling and you remove your E-beam resist. So the difference here is that if I am trying to make a pillar that is 600 nanometers tall and 30 nanometers wide, I only need to make a pit that is 15 nanometer wide, and then fill this void, remove the top, and then I have the nanopillars. That is basically the claim to fame for Capasso's stuff is to come up with this damascene process using TiO2 to make large nanopillars, long nanopillars like this by backfilling voids, right? If you try to take a TiO2 film and you try to etch it with standard lithography, you will never get this. It's impossible. You will always get tapered pillars, as shown here in Tantala. You can see we tried working with Tantala, and we are working with it currently. And if you etch Tantala, you can see that you get this big taper, right? Right, as you etch them. So etching fundamentally, except silicon, you always get some taper. But if you use the damascene process, that is a way to get around from this this problem of tapered side walls.
So one more question. In one of your slides, you showed the pillars which are hollow from inside. So what is the advantage of those hollow pillars compared to solid?
So the idea of hollow pillars is if I have a cylindrical pillar, then I only have 1 degree of freedom, which is the radius of the pillar. Okay. If I make a hollow pillar, now I have 2 degrees of freedom. I have the inside radius and the outside radius. Okay. What people do is they put another pillar in the center of it. Okay. So now you have a cylindrical pillar with a donut outside of it. So now that gives you 3 degrees of freedom, right? So you have radius of the inside pillar, you have the gap, and then you have the outside radius. So the more degrees of freedom you have, the more design choices you have, right? That's kind of the summary, right? It's basically how many degrees of freedom you can have in your simplistic building block. And we work mostly with building blocks that are either rectangular or cylindrical or square, but you can indeed make pillars that are non-arbitrary, such as the hollow pillars or hollow pillars with another hole in it or a plus sign in it or whatever, right? So it's just basically the number of free parameters that you have, right?
Thank you, sir.
Dr. Amit.
Yes.
Hello.
Yes, I'm here. Yes, I can hear you.
Yeah. So can you give some example of like in sensing? So particularly for your explosive sensing. So can we design some, or maybe we can fabricate on-chip metasurface for the explosive sensing, because they have their signature in near IR or some far IR, right? So
right,
they can
right.
be a good.
So if you're trying to make a sensor, then you I'll show you quickly. As I kind of briefly mentioned, I didn't have time to get into this in very much detail. Well, if the goal is to make a sensor, then this is what you want to do. Come on. Guys, what happened? Sorry. Here. Okay. So in this slide, right, if you can see, I have a nano pillar, and then I hit a resonance. Okay. So this resonance turns out is a resonance of an individual nano pillar. Okay. Hey, but if I make this pillar in an array, then there's an array resonance as well, which is called sort of diffractive coupling between this. And then what that does is, if you choose the pitch correctly, then what you can do is shrink the line width of this resonance very, very small. Okay. And there is a condition called the IC condition where you can almost get infinity Q. Okay, so you can get very, very high quality factors with dielectric resonator based metasurfaces. We don't work with high quality resonances because that's not our goal, but there are a lot of groups that work with high quality resonances. Okay, so if you make an array of these nanopillars and you choose the pitch correctly and the width correctly, then now you have a very, very high quality factor resonance. Okay, so now you have made a device that shows a very sharp resonance at a particular frequency that you want. Now, if you're trying to make a sensor out of it, then all there is to take a metasurface that looks like, say, this here shown in an SEM image, okay, and functionalize your surface such that if an explosive molecule comes, when it binds, it is going to change the local environment, and that is going to shift the resonance frequency, right? It is not very difficult to envision a system where one can make a sensor out of it. And notice the other thing is that these nanopillars have huge surface areas, right? They are very, very long. They have 4 sides and a top. So compared to a plasmonic system, in a plasmonic system, the surface area is very small, right? Because you're only working with one surface. And because they are lossy, your quality factors are very, very low, right? When you go to dielectric based systems, the quality factors are much, much larger. And then you have a lot more surface area, right? So in summary, I think a dielectric based system is much, much more suitable for doing sensing kind of experiments, because you can A, both get high sensitivities, and B, you have larger surface areas compared to a plasmonic system.
Thank you.
So compared to plasmonic system, what are the limitations of dielectric? Is there anything in which plasmonics are better than dielectric?
The plasmonics are better than dielectrics in confining light to very, very small length scales. So if your goal is to get a very, very high intense light spot at a nanoscale volume, so if I take 2 nanorods and I bring them close, then I get a hot spot, sort of this lightning rod effect, they call it. So you can have fields in that hot spot, let's say of bow tie antennas or nanorods, dipoles, that are thousands or factors of like millions higher than your incident field. So you get very high fields. With dielectric resonators, you are never going to get that kind of fields. Okay, so what do you need a field for? If you are trying to, let's say, surface enhanced Raman scattering, okay, for SERS you need high fields because this is a nonlinear phenomena, right? You are taking a pump photon and you're generating your two sidebands, if you would, right? Right. If you're trying to do nonlinear optics, yeah, plasmonics is great because you have very strong fields in a very small volume, right? Where dielectrics are good is if you're trying to get high quality factor resonances, you're trying to get low sensitivities and low losses, and for device level applications, if you would. Lithography is easier. Plasmonics is only good for confining light to very small length scales, right? That's just fundamental to plasmons, right? But they are very lossy, right? So it comes with a problem, right? In one case, you shove more light to a small spot and you lose a lot of it. In another case, you sacrifice the confinement for higher quality factor, right? So it's sort of like, depending on your application, one may be suitable, one may be not suitable. But I think for sensing applications, and unless you're trying to sense single molecule from a very enhanced field, right, dielectrics may be probably do equivalent, if not better job than plasmonic systems.
So, is there any limitations offered by silicon structure in NIR?
Silicons are fantastic, right? This is low loss near. So silicon band gap is 1.1 microns, right? Okay. So if you are working in near IR, so when I say near IR, I usually say 800 nanometers or so, right? In that ballpark. Is that what you mean?
Yeah, from 800 to 1500 in that range.
Okay. So 800 to 1100 silicon is lossy. From 1100 to 1500 silicon is not lossy. Okay. Right. Because the band gap of silicon is 1.1 microns, right? So above band gap. But notice that in a dielectric metasurface, you are only going through few hundred nanometer worth of material, right? So the amount of material that you're talked to is basically non-existent, right? So losses really don't matter much, right? That's why if you look at some of the papers on silicon metasurfaces, people show operation all the way down to 400 nanometers, right? So you will be like, oh, well, how does that work? Because 400 is way above the band gap of silicon. So how does that work? But turns out it works because you are not going through too much material, so you can handle that much loss, right? But ideally, if you're trying to make a metasurface out of silicon, you would want to work in the IR regime, right, above the band gap, and then you can get very high quality factor.
Thank you, sir. Yeah, you can ask question. Yeah,
please unmute.
Yeah, please unmute your mic.
It is not unmuted.
I can hear you now.
Your mic is off. Sir. Your mic is off. Kindly unmute yourself.
Unmute from here?
No, sir. Only he can unmute himself.
Okay.
Let me try. Yes, sir. Hello.
It is not unmuted.
Now is it unmuted?
Now you are audible, sir. Again muted.
Yeah.
Yeah. Are you listening?
Now I can hear you.
Hello.
Yes, I can hear you.
Okay, you can hear me.
Yes.
So I want one question regarding the diffraction effect. How you control the diffraction effect, because the size is very small, of the order of less than wavelength. Please explain.
You are absolutely right. If you look at my plot here, I'll show you one slide in a second. Here, this particular one. This is my metasurface, And you can see that because the sizes are small, and whenever I do this 0 to 2 pi phase jump, there is diffraction, right? So if I look at the far field, if I take a lens and I look at the far field, it will not look like this.
Yeah.
Okay, I will only see a beautiful Gaussian, whereas for a metasurface, I see these diffracted orders, right? But if you take this image and you go to the focal plane, this is far field. If I go to the focal plane, all of these diffracted spots, they actually constructively interfere at the focal point. So indeed, diffraction or non-ideal, scattering, whatnot, is an issue. But turns out that all of these diffracted orders meet constructively when you go to the focal point if you're trying to make a lens, for example, right? So this is a non-ideal transmission from a lens you would expect, but turns out that when you go to the focal spot, all of these diffracted orders constructively interfere and give you a beautiful Gaussian, like I showed you before, right? Does that answer your question? Sorry.
Yeah, second thing is, when the size is less than the wavelength, the light is itself circularly polarized, what I understand. Maybe I'm not sure.
No, not necessary. No, not. The device size is smaller than a wavelength, but light is still a plane wave, right? So we are not doing anything to the light. It just comes, there's an antenna effect, light goes into the waveguide and comes out.
Okay. Really, I thank you. Your lecture was very wonderful. But the only thing is, we are not copying with you. You are given so many details, and it is a very advanced field. I thanks a lot. It is a really, I enjoyed the lectures.
Oh, thank you so much.
Thank you, sir. If anyone have any question, they can unmute themselves and ask question. Okay. So I ask Amit to kindly thank our speaker. Amit.
Hi, how are you, Amit?
Thank you once again for your wonderful lectures.
Thank you, Amit. I appreciate it. I appreciate the invitation.
Amit, thanks a lot for your very nice lecture. Very informative and very comprehensive. Really, I hope all the audience got benefited out of it.
Oh, thank you, Dr. Tiwari. Yeah, we'll keep in touch. Yeah,
I'm really grateful to you, and we'll keep in touch, and then I'll share with you some designs so that we can get some fabrication.
Absolutely, right? Yeah, definitely. Yeah, we are starting to get started here, so definitely.
And we'll discuss something more, like if you have some more design, like what you have explained today, also, right? So yes. we are looking at the this explosive, or maybe for some narcotics sensing, right?
Okay. So definitely.
Yeah, and that is Sierra based.
Okay. Yeah. Definitely, yes.
So we also thanks to our Professor Sinha, our former director, and Colonia sir for joining us.
Yes, thank you everyone for joining. Yeah, I appreciate. Okay, all right, bye.
Thank you.
Bye.
Sir, can we have a digital selfie?
Yes.
I request everyone to kindly switch on their camera so that we can have one selfie with our speaker.
Sir is also there. Good evening, sir.
Good evening. I hope I am audible as well as visible there.
Yes, sir.
Yes.
Okay.
Good to see you, sir.
Okay. Good. I enjoyed your lecture. It has a wide coverage, lot to learn for all of us.
Okay, sir. On count 3, we will take picture. 1, 2, 3. Thank you. Thank you, everyone.
Thank you, sir.
Thank you, our speaker, Dr. Amit. I like to thank Professor Ravindra Kumar Sinha, our mentor and my PhD guide. I like to thank Dr. Umesh Tiwari, our chapter advisor, and all team members of SPI. Thank you, everyone. And I'd like to thank every participant to spare their valuable time to attend this informative lecture. Thank you, everyone. Thank you. This meeting
Thank you.
is done.
Okay. Thanks so much. Bye-bye.
Bye.